Hello everyone, my name is Kwarta, and today I would like to share with you the outcomes me and my advisor, Professor Matthew Allen, obtained recently in our research on the nonlinear system ID. The title of my today's talk is NIXO-Based Identification of the dominant terms in a nonlinear equation of motion. This presentation consists of 4 parts. I will start with a brief overview of how the NIXO methods work. Then I will focus solely on a new feature of NIXO, namely its black box identification capability. Then I will share with you the outcomes we obtained from 2 case studies, one numerical and one experimental. My talk will be finished with the summary and future steps. So let's begin. I would like to start with a quick explanation of how the NIXO algorithms work. First of all, NIXO is an abbreviation from Nonlinear Identification through Extended Outputs. To identify a system with NIXO, one must follow 3 steps. First step is naturally to take a laboratory measurement of the forcing signal used to excite the structure and the response generated by the mechanical system. Then we must postulate a form of the nonlinear equation of motion. This equation can be proposed via an educated guess, engineering judgment, or any other technique that allows to postulate the nonlinear equation of motion beforehand. The third step of our procedure is providing the signals to the NIXO-based formula and solving it. As illustrated on this slide, the solution consists of the linear frequency response function as well as the estimates of the nonlinear parameters assumed beforehand. If you are interested in learning more about NIXO, please refer to our last year's IMAC paper, where we explain different NIXO methods, plus we provide a detailed derivation of this formula. Before we move forward, please keep in mind that there are 2 versions of NIXO. First one estimates the nonlinear parameters as complex numbers, while the other one enforces them to be found as real. To finish this brief overview, I would like to mention that NIXO can be classified as a frequency domain identification algorithm among previously proposed methods such as NIFO or CRP. However, please note that the nonlinear equation of motion form must be known explicitly before using these 2 methods. The goal of this talk, however, is to introduce NIXO as a reliable black box system ID method, so a method which can be used when the equation of motion form is not known beforehand. Before we dive into this topic, I would like to also mention that, to the best of my knowledge, the most mature black box ID methods available nowadays is NARMAX, supported by either neural networks or a genetic algorithm. When it comes to the black box side of NIXO, we observed an interesting pattern while testing it in several case studies. Namely, if the tested structure is excited with a swept sign, plus when it oscillates at low, however sufficiently high amplitudes, then the nonlinear terms that are dominant in the system's response will be estimated by NIXO as what we call strongly real valued. In other words, NIXO will not only return the coefficients values, but it will additionally point out the smallest set of the terms that should be kept in the nonlinear equation of motion. Some of you are probably wondering what it exactly means that the parameters are strongly real valued. Before answering this question, let me first introduce 2 indicators, delta star and delta double star. The definitions of these indicators are provided in these 2 formulas. I hope that you still keep in mind that there are two versions of NIXO. First one that estimates the nonlinear parameters as complex numbers, and the other one which enforces them to be found as real. These two solution types are represented here respectively with the beta complex and beta real coefficients. Hence, delta star expresses the relative difference between the coefficient that was enforced to be found as real and the real part of the complex one. On the other hand, delta double star is defined as the relative difference between the real and imaginary parts of the complex solution. Now, with delta star and delta double star defined, we can clarify what the term strongly real valued means. Namely, these beta coefficients are considered to be strongly real valued when delta star is a small number, what indicates that beta real and beta complex are consistent, and when delta double star is close to 100%, what gives that the imaginary part of the complex solution is relatively small. These two accuracy criteria could be expressed with, for example, these two inequalities. Note that they must be satisfied simultaneously. Let me illustrate this black box identification strategy on a case study. The numerical test is performed on a curved clamped beam, which geometric dimensions, as well as mechanical and model parameters, are known. The beam is modeled with a 3-mode ROM, and it is excited with a uniformly distributed sinusoidal force. Since the nonlinearity is represented here with quadratic and cubic terms, plus the ROM consists of 3 modes, there can be up to 16 polynomial terms in each equation of motion. Since we would like to identify the first nonlinear mode of this beam, which linear natural frequency appears at approximately 65 Hz, the system is excited with a relatively slow sweep with frequencies ranging from 1 to 115 Hz. The structure was identified via providing various pairs of signals to the NIXO algorithms. The optimal results were obtained from a case study where this pair of signals was used. As we can see on the adjacent chart, the signals come from sufficiently high, yet still relatively low amplitude vibration tests. By saying the optimal results, I meant that the smallest set of nonlinear terms, which should be kept in the nonlinear equation of motion, was identified as strongly real valued. This smallest set consists of 4 following parameters: alpha 11, alpha 12, beta 111, and beta 112. Note that the delta indicators corresponding to these coefficients only satisfy the accuracy criteria mentioned earlier in this talk. Additionally, we can see that the underlying linear system was identified successfully as well. To conclude this case study, we started with a full equation of motion. As a result, NIXO pointed out 4 dominant terms which should be kept in the equation of motion. Plus, it estimated their values with a high accuracy, as indicated in the adjacent tables. To prove that the polynomial terms pointed out by NIXO are dominant in the system, we compare the true NNM, represented here with a blue curve, with the one computed for the EOM with the reduced set of the nonlinear terms, red curve. These NNMs were computed using the MHB algorithm using 5 harmonics. As illustrated in the chart, the curve obtained using only the dominant terms matches well with the true NNM over a large range of the motion amplitudes, up to 2 times the beam thickness. Moreover, if the dominant terms are excluded, then the normal mode is vibration level independent, what indicates that the system starts behaving linearly when the dominant terms are removed. When it comes to the experimental case study, we can conduct the sweep sign test in at least 2 different ways. We could collect the signals directly in the lab tests. However, the accelerometers attached to the beam turned out to have a significant impact on its dynamics. Another idea is to generate the noise-free sweep sign signals using the NNM backbone measured experimentally, together with the SNRM model function, which is presented here in this formula. The experimental case study presented on a couple of next slides uses the signals generated in the latter way. This case study is performed on a flat beam which was manufactured from PLA using a 3D printer. Its geometric dimensions and linear model parameters are known and presented in these tables and figure. As already mentioned, the SNRM model function, together with the first NNM backbone measured experimentally, are used to generate these 8 noise-free sweep sign signals. On these 2 charts, we can see a displacement and velocity responses measured at the beam's center versus sweep frequency. The true backbone is marked here with a black dashed line. These signals are further provided to the NIXO algorithms in order to identify the flat beam. Multiple case studies were conducted on. They differ from one another with the number of signals provided to NIXO and with the form of the nonlinearity assumed a priori. Namely, we tested the effectiveness of this black box strategy when different pairs or triples, as well as selected 4 or 5 signals, are provided to NIXO. When it comes to the different forms of the EOM's nonlinearity, we assume that it consists of either all the nonlinear stiffness terms or of all the nonlinear stiffness and damping terms. It was observed that in this particular case study, the optimal results were obtained when the signals were provided to NIXO in pairs and the assumed nonlinearity contained all the nonlinear stiffness terms only. The nonlinear equation of motion identified by NIXO is presented here in this expression. As we can see, only one nonlinear parameter, namely beta 111, was identified as strongly real-valued. This result was actually expected, since the tested beam was flat. Before focusing on the nonlinear part of the structure, let's first have a look on how the NIXO methods managed to detect the underlying linear system. A comparison of the true frequency response function to those identified by the algorithms is presented in the chart. As we can see, the true FRF and those found by NIXO are comparable. Moreover, the relative difference between the true and estimated linear natural frequency and damping ratio is lower than 9%, as shown in the table. When it comes to the nonlinear part of the system, NIXO found the value of beta 111 as a number between 1.3 and 1.6 times 10 to the power of 13. To validate these findings, we computed the NNM curves corresponding to this nonlinear equation of motion and 4 different beta 111 values from this range. The curves are computed with the MHB software using 9 harmonics. They are further compared to the NNM backbone measured experimentally, as illustrated in the chart. As we can see, the prediction matches the experimental measurements to a satisfactory extent. However, there are still some spots where the match could be better. This work proposes a new black box identification strategy using the NIXO type algorithms. The concept was proven to be working well on various numerical case studies. When it comes to the application to the real-life structure, NIXO seems to identify the nonlinear system to a satisfactory extent. However, there still might be some room for improvement. I would like to propose 2 future steps. First one is to employ this black box technique to identify a curved beam, and the other one to test the algorithm on a case study involving a more complex mechanical system. That's actually all I prepared for today. I would like to thank you for listening, and I also look forward to your questions. Thank you.